Hello there. So this is the second video of section 1.5, and we're just going to pick up right where we left off last time. So you might recognize this example on the board because it is very similar to the example we looked at in the first video, and that is because it is the exact same problem we looked at in the first video. So the reason I want to come back to this problem is because this video, I don't want to really introduce any new methods of solving a homogeneous linear system. We talked about that last time. I want to instead focus on a way we can describe solutions to homogeneous linear systems in the case that they have a non-trivial solution. So remember that since a linear system had, or a homogeneous linear system in specific, had a non-trivial solution when there was a free variable, remember this implied that if there was if there was at least one non-trivial solution, there are actually infinitely many non-trivial solutions. Again, I want some way to describe them, right? And so you might remember questions similar to that asking you to describe something in previous sections. This means we want some compact way of representing what all of these solutions look like. And we're going to sort of figure out a way to do that here. So remember, I can solve this homogeneous linear system given the coefficient matrix A by row reducing the augmented matrix. And so now I did this in the last video, so I will leave the work for past me and tell you that after row reducing this augmented matrix, I got the following. If I recall, this wasn't extremely easy for me as I did make a somewhat minor error. And so if you remember, this augmented matrix corresponds to the linear system of equations that I will write down here. And so remember here, x3 is a free variable. x1 and x2 are fixed or non-free variables if you prefer. And so remember, I think the solution we had talked about last time, well, since x3 is free, I can in a sense pick any value I want for it. And so I picked 3 because I think that was going to eliminate most fraction work for me. So x3 could be 3. x2 is always going to be fixed at 0 from this second equation here. And when x3 is equal to 3, I can solve for x1 and get that it must be equal to 4. But of course, since x3 is free, I can pick whatever value I want for it, right? So there are actually tons of solutions to this linear system depending on what value I want to pick for x3. So an alternate way of expressing the solution is to actually solve for each fixed or non-free variable in terms of either some sort of constant or 0 value, or in terms of, in the case of x1, the free variable x3. So this equation right here will tell me all I need to know if I want to describe all solutions to my linear system. So I know that every solution to my linear system, so we'll say describe solutions, any solution to my linear system, well, remember it's going to, actually I think I'm going to need a little more room here. So if I want a solution vector x that assigns values to x1, x2, and x3, what do I know? Well, the first thing I know is that x2 has to equal 0, right? That's from equation 2 here. I know that x2 has to equal 0. So next thing I know is that x3 can be whatever I want it to be, right? x3 is a free variable. That means that I can just pick some real number and x3 can be equal to that real number. And so let's say I just pick some real number t. I'm just going to let x3 be equal to t. And so I'll write that down here as a note. Here t is in a set of real numbers, and we're going to suppose x3 is equal to t. So we've assigned this just real number that I picked t to be equal to x3, because x3 is a free variable. Well, once I've picked x3, I know exactly what value x1 has to take on, right? So here, x1 is going to take on the value 4/3 t. Well, 0 times anything is equal to 0, so I can actually factor out a t, right? T is just a scalar, right? Just a real number. So I can factor out a t and rewrite this as the vector 4/3, 0, 1 times the scalar t. And what I've just done is I've actually described all solutions to my linear system, right? Because what this vector scalar product tells me is that every solution to this linear system of equations defined by this matrix A has to be of the form 4/3, 0, 1, so vector, times some real number. So I will write this a little more formally because there are a few more things I want to say about this type of solution. So what I'm going to do is I'm going to erase this pretend matrix row reduction work. So the solution of x equals 4/3, 0, 1 times t. So expressing a solution in this form, where here t is a real number again, is in parametric vector form. And so this is where we express or describe, if you prefer, all solutions to a linear system of equations as the sum of these vectors, which correspond to free variables, times scalars t. Sometimes we'll just go ahead and use the variable x3 there in place of t. What's important is that here I've got vector times scalar. So what else do you then notice about this solution? Well, one thing is that this means that all solutions are vectors in the set span (4/3, 0, 1). Right? Because all this set is the set of all scalar multiples of this vector. And that's exactly what this solution is telling me, is that any scalar multiple of the vector 4/3, 0, 1 is in fact a solution to this linear system. So parametric vector form, again, we're expressing our solution as the sum of vector times coefficient sort of standing in place for my free variable. So what I want to do is I want to look at one more example here relating to a solution matrix that contains multiple free variables, just so we can see how that looks. And then I'm going to go through one more example of how we can actually use this parametric vector form to talk about non-homogeneous linear systems. So suppose A is the following matrix. One, 0, 3, 2, 0, 0, 1, 4, 3, 0, 0, 0, 0, 0, 0. Express all solutions to AX equals 0 in parametric vector form. And so notice here, I've chosen to save a little bit of row reduction here, since that's not the exact topic of this video. I've chosen a matrix that's actually already in reduced row echelon form. So we can just immediately skip to the step where we write the system of equations out. And so notice this reduced row echelon matrix would correspond to the following system of equations. Oops, sorry, that should be a 2. Where here, x1 and x2 are fixed or non-free variables, x3 and x4 are free variables. So, to express this solution in parametric vector form, first thing I want to do is solve for my non-fixed variables. So all that means is just moving the free variables to the other side of each equation. And so now notice I've got x3 and x4 both as free variables. And so I can choose whatever values I want for x3 and x4, and it doesn't matter, right? I can choose one and choose the other, and those choices can be completely independent. So to express my solution in parametric vector form, what I'm going to do is I'm going to have one vector for each free variable. And that vector is going to represent the correct coefficients assigned to all of my variables corresponding to the free variable I chose. So here we'll suppose x3 is equal to t and x4 is equal to s, where t and s are real numbers. Again, just representing whatever I chose t and s to equal, or sorry, x3 and x4 to equal, since they were free variables. So first, I'm going to create a vector for x3. So whatever value I chose for x3, I should multiply -3 times that when calculating x1. Whatever value I choose for x3, I should multiply -4 times that when calculating x2. Well, x3 should equal 1 times itself, and x4 does not depend at all on x3. So there would be my vector relating to x3. And then I just do the same thing, but for x4. Oops, and I think no, that's correct, yes, okay. And so this would be my solution in parametric vector form. So here, notice, now every solution is a linear combination of these two vectors, where I'm just choosing any two arbitrary real numbers, t and s. And so in fact, notice now any solution to this is the span of these two vectors. And so it will just be, again, any linear combination of the two vectors I choose. And so really cool, actually. I could choose s to be 0 and t to be 1, and this vector alone should give me a solution or a non-trivial solution, right? Or I could choose t to be 0, s to be 1. Again, any real numbers s and t I choose will give me a non-trivial solution to this homogeneous linear system. But so this here way of writing out this solution or describing all solutions is called parametric vector form. All right, so I want to do one more example. It'll actually be very, very similar to what we did before. So what this example is going to be is actually how we can use parametric vector form to express solutions to non-homogeneous linear systems. So you might recognize this matrix A from before. -3, 6, 5, -2, 1, -4, 4, -8. And we're going to jump back a section or two, and we're going to let B be the vector 7, -1, -4. And so what we want to do is describe, I think I wrote describble. Describe all solutions to AX equals B in parametric vector form. All right, so you might notice this is the same matrix that we had from before. So what I'm going to do is I'm going to row reduce this because I think or row reduce the augmented matrix that we should be row reducing here. And the reason I want to do this is because I think it will be an interesting example of the what I was describing last video, that this last column is going to have no effect on what what my final row reduced echelon form is. So the row reduced echelon form, the first 3 columns here are going to be identical to the first 3 columns when I had zeros here. So I might move through this a little more quickly since this will end up being the same sequence of steps that we used last time. But you'll have to be very careful to check my work on the last column because unfortunately now the last column doesn't just contain zeros. So again, first things first, I want to completely clear out that first, this first column here beneath the 3. It should be -9, -4, 0, 0, 7, 6, -18. All right. Then what I'm going to do, I'm going to, let's see. I'm going to do these steps at the same time. I'm going to do -3 row 2 plus row 3. And then I'm going to do 1/3 times row 2. And so notice doing -3 row 2 plus row 3, I actually completely clear out, or sorry, 3 row 2 plus row 3, not -3 row 2. 3 row 2 plus row 3, I completely clear out row 3. And then dividing through by 3 here, I can get the leading one that I want in that position. And then so all I have left to do after this, well, I'm going to do -5 row 2 plus row 1 and replace row 1. Oh, that shouldn't be 0, that should be 3, 0, -4, -3, 0, 1, 0, 2, and 0, 0, 0, 0. All right, and then I just want to do 1/3 row 1, and I get my row reduced echelon form matrix. And so you might notice at this point that, in fact, the first 3 rows of this matrix, or first 3 columns of this matrix, excuse me, are completely identical to the first 3 columns of the matrix I got when I was solving the homogeneous system corresponding to this matrix. So, how do I express this in parametric vector form? Well, notice that, again, this corresponds to the following system of equations. Except here, of course, I have non-zero terms on this side of the equation. That's okay. I'm still going to do the same first step where I solve for my non-free variables, or sorry, yeah, my fixed variables. And so what I'm going to do is I'm just going to add one more vector, right? So again, I'll suppose that x3 is equal to t, and I get the same first vector, right? So if x3 is equal to t, then I get the same first vector I got when solving the homogeneous linear system. But notice x1 is equal to 4/3 x3, so 4/3 times t, minus 1. So all I need to do here is add a vector of coefficients to account for this. And so notice specifically this vector, -1, 2, 0, is not being multiplied by any sort of constant. But if you read this vector straight across in each row, you'll get exactly the equation that we should get, except of course we will add that x3 equals t. So this is parametric vector form for a non-homogeneous linear system, as opposed to the previous example, which was parametric vector form for a homogeneous linear system. I actually think this wraps up section 1.5. So at this point, we should be done. This should be the last video of week 1. I will make an announcement about this on Canvas. I think I should have at this point a short, ungraded sort of just evaluation course, or not course, a short quiz. It's called the plus delta feedback tool, I believe. It has 4 questions, which you will answer anonymously if you choose to do it, where you can just give me feedback about how the course has been going, what's worked and what hasn't worked so far in terms of your learning. And so that will allow me to, moving forward with this, continue to try to make the course better so that you can learn as best as possible. Because, of course, this online learning and sort of method of teaching is very new to a lot of us. So I will see you next week for section 1.6.